Now let's have a closer look how addressing is really done. We start with IP version 4 because a lot of traffic in the internet still uses this rather old addressing scheme, so you should know how this works, and we'll learn a lot about what could be done better, and then we'll look into IP version 6. So the Internet Protocol IP, that really gives the name to all this TCP/IP protocol suite. These are our 32-bit addresses you all know, an example address. And those addresses, they have two parts. One is called the network part, and the other is the host part. And the network part is the important part for our aggregation. Remember, we want to aggregate, and this is the part, generally speaking, routers in the internet have to know. Routers in the internet, they do not care about the host. They do not care about any networks inside, for example, the campus of a university or of a company. No one cares outside. Outside, it's important the routers have to know the network part, and those so-called network prefixes, well, there are hundreds of thousands of them. You can also represent this in a binary fashion, so you have the binary representation. So these are our 4 bytes, 32-bit classical IP version 4 addresses. We have different types of addresses. They all look the same with the 4 bytes, but the typical addresses are our public IP addresses, and they have to be unique. That's the vast majority of the addresses, so unique public addresses. And typically, all the nodes in the internet, they have to have at least one public IP address. Well, there's a strict definition of the internet that says you have to have at least a public IP address. But there are exceptions, not in the strict definition, and many people say, okay, if you do not have a public address, but a private address, then you're not really part of the internet. And this is true to some extent, as we will see. Private addresses, they are not unique, and thus you cannot really route them globally. What is a private address? We'll see these are special address ranges, so addresses that start with 10 dot and then X, Y, Z, whatever you have here. So also this notation, we'll learn what this means. So you have certain address ranges, and quite often if you look at home in your network, what is the IP address of my device? You will then find something, oh, my device has 192.1.12. This is a valid IP address, but it's not a public IP address. And thus, strictly speaking, your device at home is not part of the internet because it has no public IP address. We will learn why we use the private addresses, what the reason for this is, and what happens. I mean, they are not globally routable, so how can we then reach the internet? We will see that there's a device called Network Address Translator that translates this address into a global, routable, whatever IP address. We'll also learn that this is not the best idea, but there are certain reasons for doing so. Okay, so public IP addresses, that should be the standard case. Then there are the exceptions. We have some private IP addresses, 3 address ranges, not routable. So all the routers will simply drop those packets. They don't know where the destinations are, so no idea. Then we have some special addresses, so-called, for example, loopback addresses. Loopback addresses are quite nice. So, for example, if you want to test something, then you have your normal socket interface, and then you can test something, and then later on you can replace this by some other address. For example, we will also learn that there are some different other types like multicast addresses, IPv4 6, some link local addresses, and so on. So we will see what these special addresses are. For now, it's important that you know there are public addresses, majority, some private addresses, some special addresses. And routers, they have typically connections into several networks. Then they have an IP address for each of the network. And as we already saw, the addresses are composed of two parts. One is the network identifier. So that's for the network. That's our prefix. That's the important part for the internet, for the routers. So they have to know something about the prefixes. And then the second part is the host identifier. Okay, so how does it now work? Simple example with a small network with a router in between and one network. That's the network called 192.168.13.0. So that's the address of the network, not of a special computer. And then on the right hand side we have 147.216.113.0. So we have two networks, and now we have computers in the network. And now if you want to send something, you will see that here on the left hand side, these are the addresses. Remember 192.168. These were the special private addresses. But independent of that, so if you want to send something, you send your data. For example, if this computer A wants to send something to the computer B, sends the data across this router inside the network reaching this computer. What is needed for this? Many things. One is, here in this case, if you have private addresses, we have to translate somehow. The router, a pure router, cannot handle these addresses. We will learn that we need some network address translation if we want to handle these private addresses and want to do something. What this is, there's a special subsection for network address translation. Furthermore, we'll see that the router has to store some parts. So has to know, for example, where, over which interface, in this case, do all the packets go towards this network 147.216, 113, etc., etc. So 113 and so on. So we have to learn something about network prefixes, aggregation, later more on this. What else? How do we know inside the network? Assume maybe we have a switch here, with or without switch. How do the packets know if I want to go from A on the left to B on the right? How do packets know that they go across the router? What is underneath layer 2? Layer 3, there's layer 2. So we have the IP layer 3. We have a source. That's our A. And that has this 192, 168, etc. Yeah, we have to do something with that. We have a destination. That's 147 to 16, 113, 71. Okay, that's B. Okay, now that's the IP layer. We know we do this layering. So this is then inserted as payload. We know this. So yes, we also have some user data here, also user data here, but that's all payload for our layer 2. Layer 2 does some frame check sequence, etc. But now the important part, layer 2 also has MAC addresses and some other fields. We know how Ethernet looks like, but there's also a destination MAC address and there's a source MAC address. Oh, source is easy. Source, that's the MAC address of A. This is MAC A. Perfect. What is the destination? And now many people think, well, somehow we have to find out the MAC address of B. No. What we have to find out is exactly this one. We have to find out the MAC address of the router of this very specific interface, 1. There's also interface 2. Both interfaces have their MAC addresses. So we will see that on layer 2, we send our Ethernet, for example, packets from our MAC address MAC A to the MAC address of the router interface 1 in this example. Because we have here our layer 2. This is where we have our layer 2. That's layer 2. It starts at computer A, it ends at the router. And in this very simple example, we have yet another layer 2 starting at the router, here starting at router interface 2, and ends at MAC interface B. There is no layer 2, whatever association connection going across a router. So the layer 2 starts in my computer, ends at the router. So if you send a packet from your computer at home to whatever computer worldwide, the destination MAC address is the MAC address of the interface of your router. Okay, and the IP address, they handle the end-to-end issue. So you see these hierarchies. So we have layer 2 and layer 3, and somewhere inside layer 4 and higher. Okay, so now let's go to how do the addresses look like. And yes, I'm fully aware we start with an outdated classing scheme, but that's what you find not only in all the textbook, but that's also what you have to know in the background. This is how it all started. I will quickly go through this and then you will understand why we don't use it this way anymore. So first of all, we have a definition of 3 classes of networks. 3 classes of networks with a difference of how long is the network part. Remember, we had a network and a host part. Class A, Class B, and Class C. And we have special bits that tell all the systems what class this address is. Class A, B, C, depending on the first bits here. And following the network part, we have the host part. So what does it mean? For class A, we have a small network part that allows only 426 networks, but many hosts. So class A addresses is for someone who has 2 to the power of almost 24 hosts, which is quite a lot. No one has that many hosts. But why has this been done this way? No one expected the internet to explode in terms of numbers of hosts, etc. So there were some years ago still organizations holding class A addresses, but never ever did they have millions of computers. Class B means at least 16,000 networks with 2 to the power of 16 hosts, or 65,000 hosts, and class C means you have millions of networks with 256 hosts. That's always a bit less because there's a special address for the network, as we saw on the slide before, and a special address for a broadcast within the network. So these are the classical classes A, B, and C. And then there was a definition for multicast. We'll come back to multicast. So multicast, that means one sender sends to a group of receivers and some reserved addresses. So this was the classical scheme, and using the classical scheme, you could address arbitrary computers, like for example, web server of our university, where you see, okay, the first bits indicate that this is a class B address, and then the next bits, 6 from this first byte and 8 from the second byte, they both together tell this is the class B network ID of our university. So if you want to have a network, you have to ask later how. You have to ask for a certain class network. That was the classical way. Then you got, for example, a class B or several class B networks. So the university got 3 class B networks. And then inside the university, the administrators could do whatever they wanted with the byte number 3 and byte number 4. And we'll learn how you can further subdivide then this host part into subnet and terminal identification. That's one way of doing so. So that is the idea, that you get an IP address, and the routers in the outside world, they only have to know these first 2 bytes in this example. They don't care about all the other internal organization. There are some special addresses, well-known IP addresses, so host and the network, this host, broadcast, etc., local loop. So these are some special examples. And that was the way in the 80s, in the 90s, in the 90s and still early 2000, we'll come back to the problems. So you see the distribution of the address space per address class. And in the early days, many big organizations, German Telekom and MIT and whatever, they grabbed class A addresses, nice, but who has 16 million computers and whatever, so a lot of the space, address space, was left empty. But also, if you pick a too small network, just for example, a class C network, so you're a company and you have whatever 50, 60 computers, fine. So then a class C network is fine. Class B would be way too big. But now the company grows and now you have 500 devices. So class B, that's not enough. That class B is enough, but class C is not enough. So class B, that's too much. I mean, class B, 65,000 hosts, way too much. You waste, if you have only 500 computers, you waste 65,000 addresses. You block them. Okay, that's not a good idea. Then why not have 2 times 256? That's fine. Yes, that works. But who guarantees you that you have a common prefix? So what does it mean, a common prefix? So let's assume your company has the address, whatever, 201, and then you can do whatever you like. And then you grow, and who guarantees you that you now get 200.1.2. You can do whatever you like. Because maybe this already went to some company X. So what can you do now? So it's way more likely that you get additionally, let's say, 198.6.67, and now you can do whatever you like. So you have addresses in this range and you have addresses in that range. Is this a problem? Well, everything works, yes, but think of the idea of aggregation. Can we aggregate those 2 prefixes? No. We both have to store them in all the routers. Because if you're a company, now assume you have your company site, here are the routers in the internet connected to your company router, and now suddenly you have these 2 prefixes. The routers here have to store all the 200.1.1. whatever it is, but also all the 198.6.67. whatever it is, they all go to the company. And with better aggregation, you could have done something like, okay, maybe there's more flexibility. There's now, depending on the addresses, assuming we get them close together, 1 point, and now, depending on whatever, how many addresses you have, you could say 200.1. Now, depending on the bits, you could say all this, whatever, we will learn how this is then, the notation is, certain prefix, all these go to the company, depending on, well, how many addresses you have. So these classes, that's not really a good idea, not flexible, because the border between network and host part is always bytes. It's always byte oriented. Either the first byte is the network part and then the remainder are host, or 2 bytes and 2 bytes, or 3 bytes and 1 byte, not very flexible. So this is why since the mid-90s, the idea was, can we do this in a more variable way? So variable length masking, so networks. How does the solution look like? So VLSM, that means not using the static classes, so byte by byte, but we have an address /n. And this n means that the first n bits are for the network identification. So remember, we had this network part and the host part. And classical scheme was, oh, the border is only allowed here exactly when you have a full byte. And now you have it in a more flexible, variable way. So first n bits are for the network part, and the remaining bits are then for the host part, which is then this 32 minus n. So an example here, /17, that means the first 17 bits are the network identifier. And that again is then the part, this prefix, a router has to store. That's the network identifier. That's the idea here. And this is the base for CIDR, classless interdomain routing. So CIDR, the C, that's classless. And now you understand why classless. We do not use those classes A, B, C anymore. That's historical, but you should at least have heard it. So the two different notations are, we write explicitly the prefix length. So we write the number of bits that represent the network part from the left. So /16. Oh, this could have been this classical class B address. So 8, 16, 24. So these are exactly the borders of the bytes. Or we can also write it in the form of a explicit net mask. So telling, okay, how many bits we have here. So we have the 8 bits and again 8 bits, and then all 0. And here we see when all this sequence of ones ends, this is then the border between the network part and the host part. And this idea of this masking, this is also something that has been done before we used CIDR, this classless interdomain routing. And this comes from the idea of subnetting. What does this mean? Already when we had those classical classes A, B, or C networks, the idea was for network administrators, yes, fine, thanks, we have the network ID, that's what we've seen, what we've learned, and this is what you have to know in the internet worldwide. And then you give, for example, that was the classical for our class B, we had 2 bytes here, and then we had 2 bytes left for the host. And then this is the job of the organization that has the class B, the old class B network, to further subdivide the networks. And the idea was there already that why not giving a certain identifier subnet for chemistry, for computer science, for electrical engineering, or for sales and for production and for whatever. So, but that is something then locally. So you see on the left side, we have the network ID. That's something for the routers, worldwide, etc. And then on the right side, we have the host. And now we further subdivide inside the host into a subnet and a host idea. So the idea is that some bits of the host address part are now used to complement the network identifier. Because if you do so, this subnetting, then suddenly all this first part is now a network identifier and not a host identifier anymore. It's just a question who assigns which part. So in all the hosts in the same physical network now use the same subnet mask, and you have a certain subnet ID for the subnet of chemistry, for example, and all the computers within this then use the same network mask. And then, as we'll see on the next slide, we combine the IP address and subnet mask, and then the router knows which subnet the router has to use. How does this work? For example, we have again our address, here our IP address. From the outside world, we still see, if we follow the classical scheme, that's a classical class B address, as we've seen. But now internally, the administrator can say, wait, we use a part of this host identifier also as a network identifier. That's our subnet. And now suddenly we have more bits for the network part. Well, that's important for our internal routing, and fewer bits for the host part. So that, and you can write it either the network mask or here in this case /23. So that's the idea. So what happens in the routers? So for example, if the routers have to forward traffic, rest of the internet is not interested in this. So the routers here in the internet, they don't care. But administrators can say, okay, our router R1 that connects to, let's say, chemistry and physics or whatever departments, they have to know the subnets. And here we use very classical, simple subnet masks, this 255, 255, 255. So we can further subdivide, for example, our class B network into subnets. And one is a Ethernet in this example, subnet number 1. And there you could have certain computers with these addresses as shown. And also the router here has now an address in this subnet. And we could have another one, subnet number 2 for computer science, the other chemistry or whatever. The router then has to know that, okay, if we have incoming traffic for certain subnet, whatever, certain machine within the subnet, then the router knows where it goes. But all the other routers in the outside world, they don't have to care for whatever there is here on these bytes. So they don't care. This could be whatever there is. So they only look here at the network part. That's the important thing for all the routers in the internet. And if you then receive a quite concrete packet for a certain router, then you know where this goes. You perform this logical operation to destination address, subnet mask, so depending on where you are, and then you simply forward it and you know, oh, okay, this goes to this router. The router then has to know where to further subdivide. And there are many configurations possible. But that's the basic idea of further subdividing the network plus a subnet part to have then a larger network identifier. One is assigned globally, as we'll see on the next slide, and the other can be then handled by a network operator, by the administrator, depending on the special requirements of a company, of the network, etc. So that's a very general idea. So where do I get those addresses from? Overall, there's the Internet Assigned Numbers Authority, IANA, and they take care of the whole address range, but then there are so-called regional internet registries, like in Europe, RIPE, and they are responsible then for giving away parts of the address space to local internet registries. And the local one, those are the typical internet service providers, larger enterprises, academic institutions, etc. And they then give away parts of the addresses to their customers. That's the idea. So that's the way how you then distribute all these addresses. So the customers then finally can do whatever depending on where they get the address from. So universities typically they get from RIPE and APNIC and whatever from the RERs, the regional registries, they get their address ranges and then they can further subdivide. But if you're a single customer, then you get from your ISP your address. So what was the problem? Roughly 12, 13 years ago, IANA said, okay, we do not have any addresses anymore. So we gave away the last available block of IPv4 addresses to the regional registries. This does not mean that all the addresses are used. Remember? So if someone has a class A address, well, this institution wastes a lot of address space because you don't have these millions of computers. Okay, so why did this happen? Nobody thought about this growth of the internet. No one. So otherwise, everyone would have started with more bits and a different way of assigning addresses. So one idea was pretty soon, extend the address space. That is one of the motivations for IP version 6 that was standardized in the mid-90s. You see, mid-90s, 15 years earlier. So everyone saw the problem, but it still happened. So IP version 6 has 128 bits, so we have 2 to the power of 128 addresses, which is quite a lot. A bit later, similar thing happened then in Europe, for example. The RIPE ran out of IP version 4 addresses. And that means no more IP version 4 addresses. Well, what has been done? The address pool, as you see here, for the different RERs, you see how many addresses are left. It goes down for all of them. And so what has been done? One thing is you could free some addresses by changing, well, class A addresses into CIDRized many other blocks. But that means for organizations readdressing, etc. So it's a bit of an effort. So CIDR helped a bit. That's one way of doing it. So we stop using those classes that waste a lot, so that the used address looked more like a Swiss cheese. So that does not mean that we use all the 2 to the power of 32 addresses. But due to this class scheme, we wasted many addresses. That's one thing to do. There was a second thing to do, and that was network address translation. We'll see that many private customers, they use private IP addresses. And private IP addresses, as they are not globally routable, they don't have to be unique. So you can reuse the private IP addresses. With the help of NAT, many millions could use the identical IP addresses. That's not an ideal solution, but that also helped. And then parallel development of IP version 6 since mid-90s. So that was also one way of replacing IP version 4 with version 6. And this all together helped to get around of the problem, because as you all know, the internet is still up and running and we're not always using IP version 6, which is the better choice. Why? Well, coming to IP version 6 addressing. First the address, and later on we'll have a closer look into the protocol. Yes, many more addresses. That's quite a lot. But as we'll see later, again, we cannot address 2 to the power of 128 end systems, because we have many reserved addresses, special address ranges, etc. But before we look into this, first of all, how do we write this? Well, it's a bit more cumbersome. So we have this notation that we say, okay, we always bring together several bits, 16 bits, then colon, 16 bits, colon, etc. So 2 or 1 colon 0 db8 colon 00000, and so on. So many zeros, many zeros. That's not ideal. For machines, they don't care. Machines can easily write this, they use single bits. But we as humans, we don't like this, so we can do several things. First of all, we can replace consecutive blocks of zeros by this double colon. So remember, we had this 0, 0, 0, 0, colon, 0, 0, 0, 0, colon, and so on. So we replace this. That's one way of doing so. What else can we do? So this is where all these zeros went. We can simply drop the leading zeros here and simply only write the 1. And this really makes it a bit more compact. But you have to know how this is done, then you know what this address really means, so that there are many zeros in it. With the help of IPv6, we can do also fancy things, like, if you don't know German, the German word for monkey. Okay, but we can also do some serious stuff with it. So, what types of IP version 6 addresses do we have? We learned for version 4, we had global, we had private, we had some multicast addresses. Here it's quite similar. Most of the addresses, all the others, these are our global IPv6 addresses. And we have many of them. But we cannot use all of them because we have more local addresses, unique local, linked local addresses, and our unique local addresses. So these are basically with our private addresses back. So, okay, that's something we can do. Linked local addresses, that's something special. A linked local address. That's something interesting feature. So all the interfaces of IPv6 hosts, they have a linked local address that always starts with this prefix FE80/10. Well, we have 10 bits, and then we have many zeros, typically many zeros, 54 bits that could be used for subnetting, typically set to zeros, and then an interface identifier. Now the interesting part is that the host can compute and assign the interface identifier by itself without the presence or cooperation with any external network component, like, as we'll learn later, a DHCP server. And the process then is called a linked local address auto-configuration. Why is this useful? After power up, an IPv6 host immediately has a valid IPv6 address, which is then this linked local address, and can then already use layer 3 protocols. And as we will learn, IPv4 hosts cannot. They do not know their IP address. That means they cannot use layer 3 protocols from the very beginning. They have to use some other tools, as we will see. But here with IPv6, we can immediately start. And the interface ID could be, for example, the MAC address, but today we use a hash value that identifies the network interface card so that we do not reveal MAC addresses. Then there are some other addresses, mapped addresses, where we can map IPv4 into IPv6. There are some loopback, some unspecified, but also multicast addresses. And we have something new. Anycast, I will explain. So that's basically a unicast address. So as soon as more than one interface has the same unicast address, it's called Anycast address. We have no more broadcast. We use multicast, so no more broadcast here. So how does it look like, IPv6? Well, we also have this network part. It's now called the global routing prefix. And we have a subnet identifier. So this is basically our network part. That's pretty similar to IPv4. And we have our host, our interface identifier. So the global routing prefix, that now depends on the RAR or the local registries. And well, depending on where you get your address from, you will get what we call then a /32 address. That gives you quite a lot of freedom, and certain ISPs get the /48 address. So this depends on what type of address the registries will give you. And then if you have such an address, this is the global routing prefix, and this is what the routers have to know in the internet. The prefix, they have to store all the prefixes. So we'll come back to this. Then there's also the subnet identifier, again assigned by an administrator of the university, of a company, to then create all the subnets as we know from IPv4. And then you have the interface identifier. How does it look like? For example, if you check your own DSL router, cable modem, etc., then if you do this, you see that most of the devices, they still have their IPv4 addresses. For example, here, that's a global routable address. Internally, we use the private addresses. So this is why all these devices, they know NAT. I will come back to this. And then they assign to all the internal devices 192, 168, blah, 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 for example, or 10, blah, 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 depends on the system. And then all the devices today, they also know IPv6. And the device itself has an IP address. So that's the address of the router. See, quite a long address. And then, as we'll see, the router announces also a prefix inside your local network. And then the other devices, as we will see later on, can then pick an address based on this prefix to create a valid global routable IP address, and we do not need network address translation any longer. DNS, we've seen that in previous chapters. Here DNS, we see, for example, IPv4 DNS servers, but also IPv6 DNS servers. So that's the idea. You see the configuration, and we'll learn that many devices today, they know both version 4 and version 6. They have two protocol stacks inside. We have special addresses. Anycast, that's new. Anycast addresses, they look like a unicast address, so you don't see by the syntax any difference. And well, as soon as you assign a unicast address to more than one interface, it is an Anycast address. So why do we need Anycast? So that has to do with routers. So for router identification, if you want to see, okay, which routers are attached to a subnet, or routers giving entry to routing domains, so we'll come back to this. So Anycast, basically, that means you do not send something to all computers, for example, having a certain address, but to one end system out of a group of these computers. Anycast address has a special format, but it is a normal unicast address. So what else? So Anycast addresses, and always look up in the literature if you're interested in some more details about especially this topic. There are so many, we cannot go into all the details. Multicast, I will have a special section about multicast. Here, that is now an address where you can reach a group of interfaces with a certain packet. That means the network then also duplicates the packet so that all the group members will receive the data. And you may belong to several of them, so there's a special format for this. You identify with the first bits, with the 8 ones, you identify, oh, this is a multicast address, and then you have certain flags, and the flags then tell type of a multicast, so permanent, non-permanent, dynamic, etc. I will come back to multicast, and what is quite important for multicast is a scope. That means how far should this multicast packet be sent or forwarded. So for example, you can say, okay, I have a multicast group, but this is only on my site, and this should not have a global scope, so or only in my organization. So the routers can then check based on these scope bits if it should forward the packet or not. So multicast, I will come back. Anycast is a special thing you can look up in literature if you're interested in some more details. So we are at the addresses. So what are the differences beside the length? That's quite obvious, but what are the real differences between IPv4, IPv6 addresses? We saw the basic structure of unicast addresses and who is responsible for which part when you assign a certain address. So who does this? We also saw the idea of subnetting. So why subnetting? So we have network, host, and why now subnetting? And we've seen for 4 and 6, for both, we have something like private IP addresses. Why do we need them? Do we need them? What is the idea of private addresses?